hello everybody. I will keep the time very tight because we are not supposed to miss the boat. So the first, my name is Maciek Levenstein, and I will be chairing this session. And first speaker in the session in Lars Bojer Madsen, who will be talking about matter in ultrashort laser and electron pulses.
Yeah.
Nondipole and correlation effects.
Yeah. Great. And yeah, thanks for joining after the coffee break. It's a nice meeting, even though it's a bit packed. The title here is very broad. It came to me as a surprise that I should present a title and an abstract. So this was what came to my mind. I thought this would be broad enough, but at least there is something here zooming in on the actual topics. And this is what will come now, I guess, if this one, we now know how to. Yes, now here you go, it's fine. And this is the outline. First, something about non-dipole effects in intense near-infrared and infrared fields. Then something about non-dipole effects in solids in an intraband setting, followed by some results on electron correlation effects in high-order harmonic duration, and finally a very short perspective on using ultra-short electron pulses. So that's the agenda, and I'll try to finish even before time, such that we have a little bit more time for the posters, right? Okay, so just remind ourselves what is the dipole and what is the non-dipole situation. So the dipole approximation is what we learn in textbooks in atomic and molecular physics, that you approximate the propagation factor associated with the wave number of the laser with unity. And we remember that this wave number is the laser angular frequency divided by the speed of light. So of course, if the size of what you investigate, the atom, is rather small, say a few atomic units, and you have optical frequencies, this is much smaller than 1. And normally you would assume then that this is a good leading order, Taylor order expansion. It has also been known for a long time that if you use high omegas, X-rays, whatever, and do single photon ionization, the dipole approximation breaks down. This is no longer a small number. A typical signature is prepared here. So this is now assuming you have an S state, you ionize with 1 photon, high energy photon, you would get a dipole pattern for the continuum electron in the dipole approximation. In the non-dipole case, you would get not a dipole pattern, but you'd get a shift forward in the laser propagation direction. So this here is a polarization and this is a propagation. And this has been known for many years. The new thing, which has been known for fewer years, to some of us at least, is that also for high intensity and low frequency fields, you can have a non-dipole effect. It's different in nature. It's because if you think about the quiver velocity, it scales like the field strength of the laser, which is now intense, and inversely to the angular frequency. So if this is a big number and this is small, this becomes big. V becomes suddenly no longer very small compared to the speed of light. Magnetic effects kick in. So the excursion is super large, and there is a B field component that sets in, and this is a kind of non-dipole effect we will be concerned with in this talk. And just to motivate that this is not something that I cooked up in a theory mind, I show you here 2 experimental signatures of this kind of stuff, and they're kind of representative of a large body of experiments that have come out in the recent years. This one here was the first one. You see rather long wavelengths. And here you have the photoelectron momentum distribution, the PMD. This here is the laser propagation direction. This here is the laser polarization direction, and the typical signature is that you get this long distribution along the polarization. And then the non-dipole is that if you zoom in here and look at how is it distributed along the propagation direction, there's a shift away from 0. In the dipole, the peak here in this distribution is at 0, but they observed a shift away from that one. That's something you can never get in the dipole. Another recent experiment is kind of illustrated here. This is not the data, but that's a kind of rationalization of the findings in this experiment. Here, they look at ATI spectra, and they look in the forward direction with respect to the laser propagation direction, and in backward direction with respect to the laser propagation direction. And when you look in the forward direction, what they found in the experiment was that the ATI peaks were not at the position you would expect, but were shifted backwards a little bit. And when you looked in the backward direction, you found that the ATI peaks, notice the energy here, was shifted to high energies. It's very strange and a priori not okay somehow, right? I mean, it seems to be violating energy conservation. So these are both non-dipole effects, and I'll explain these things. And for the take-home message here is that the main features are shifts in peaks and shifts in ATIs. So that's typical signatures. Now, how to write up some theory? Well, the easiest thing here, or what I will do, is to start with the Schrödinger equation on the corresponding non-relativistic Hamiltonian, but now including in the minimal coupling scheme the full retardation. So I have here the time dependence as we normally have, but then I also include here that the laser propagates in X direction. So for example, if it propagates in X, I can take it transverse and it can be polarized in the YZ plane. If epsilon here is 0, it's linearly polarized in the Z direction. If epsilon is 1, it's circularly polarized in the YZ plane. Okay, so that's well known. It's also well known how to do a first order Taylor expansion in powers of 1 over c of this object. That will create two terms, one which is the normal dipole term that we normally use, and then a correction term. And at first sight, you may think, why do I have two correction terms here with two indices? And that's because you see you have both eta here in the envelope, and you also have it here in the carrier. So if you're careful, you need to include both. But if the pulse is long enough, say more than 7 cycles, this envelope contribution is small compared to the carrier. So now we go to the next slide, where I'll show you some explicit formulas for these based on that formula there. And here's how it looks. So the carrier contribution would have exactly this dependence on the coordinate in the laser propagation direction. And here is a total Hamiltonian. You have the dipole coupling terms, you have the Coulomb or whatever potential for the electron with the ion, and then you have two correction terms to first order in the correction to the dipole vector potential. One that couples to the momentum and one that just couples to A naught. And if you like physical interpretation, you want to remember that this A naught is just the laser-induced momentum kick to the electron. So because it's the integral of the E field. So this here is like a little bit like that one, but we know that this is a dipole-induced velocity. Now, this is fine. Quite a few people have used this. It's accurate to first order in 1 over c. I have not used anything else. Now I throw a new element in, and that's an approximation related to a situation when this A1 here is large. Oh, sorry, when this A0 here is large. When A0 is large, maybe it's larger than P. So that's the approximation. That's the strong field approximation. So this leads to the non-dipole strong field approximation, which is given here. And it has been shown by us in a series of papers that this one is accurate. And now the great thing is that this is in P and this is in X. So therefore you have no longer this annoying issue with mixing X and P operators, which we don't like when we do theory. It also means that you can get rid of this one and collect a new modified vector potential with a magnetic term here. This is now the velocity gauge version of the non-dipole strong field approximation Hamiltonian, or you could express it in the length gauge with a modified field, which has the normal dipole field and also some correction from the magnetic term. So that's the theory we want to look at. The first thing you can do with this one is to write down the non-dipole Volkov states. It's kind of trivial. You have momentum states that may or may not be shifted with some appropriate vector potential. But the point here is that the phases are the same with now non-dipole corrected vector potential. The first thing we did was to use this type of thing in the short pulse limit and ask how is this momentum distribution shifted? And if you apply this kind of theory, you find this shift in the peak position that I alluded in the beginning, this one here, this shift here. is exactly found in this type of theory, so that's nice. Another thing that you can do is that you can consider the long pulse limit, and then you can do all these integrals here for the vector potential, and you get a quiver motion term, and you get a linear term in t, and you get an oscillatory term. And the new thing here is that this u prime is the normal ponderomotive potential, the average cycle average kinetic energy, but it depends now on what direction does this photoelectron move. That's the effect we're after. Let's look at a consequence of this. Here is the normal energy conservation. Kinetic energy after absorbing n photons is n omega minus up minus ip, where ip is the ionization potential. Now, in the non-dipole case, we have to use the corrected one. And if I insert the new expression for the corrected ponderomotive energy shift and rearrange terms, I arrive at this one here, which we remember from high school describes a circle with now a shifted origin. So here you see that we also can explain this type of experiment. So the physics is that the non-dipole contribution shifts the energy conserving rings with a magnitude that is proportional to UP. So if you have a big UP, you get a big shift of the rings. This is what they saw in the experiment. If you now play around with this, it's easy to do in theory. And look at how does this shifting affect the ATI spectra. You will find here that as you keep the intensity fixed and increase the wavelength, you can go from a situation where you have clear ATI peaks in the correct non-dipole approach to no ATI peaks. And that's simply because the rings, the energy conserving rings, have shifted such that when you integrate up the energy with respect to the origin, you miss the ATI channel. Good. A final point about this with the non-dipole effects in atoms is just to connect to one of the popular approaches, this kind of two-step approach where you do first a tunneling step and then propagation in the fields. And then the question is, of course, how to set this type of calculation, how to initiate the calculations. You need the exit point maybe, and you need some initial momentum. And here is a recipe of how to include non-dipole effects in this type of physics. So here you have the Hamiltonian with the corrected electric field. I now changed notation because this is from two different papers. You should never do that. You should stick to one notation. But this is the E field now with the dipole E field and the correction. The dipole E field is along Z. So this is this one here. And the other one, the correction is along the propagation direction. So at a particular instant of time, the field points here. It's not a long set, but it's tilted a bit. This means that when the field points here, the negative electron exits here. So I have a non-dipole corrected exit point. That's important when you do this type of stuff. Moreover, we normally like to take a sample over the transverse momentum. And that's now not with respect to this axis, but with respect to a slightly tilted axis. And this has to be included, and it's kind of easy to do in future two-step type of modeling. And so now we change to something. Now we change to high order harmonic generation. This we have seen. I don't want to remind you about this. I want to do first intraband high order harmonics, and because I'm interested in this non-dipole effects, and to motivate that it's okay sometimes to just consider intraband harmonics, we found a lot of references where that model was good enough, right? So I'm not saying that intraband harmonics is the only thing. I'm saying if you have, for example, rather large wavelengths, you can have many cases where it captures the physics, and it's in this scenario that we now ask about what are the non-dipole effects for this kind of stuff. And for doing that, when you do the intraband, it's good enough to consider the semi-classical equations of motions that we know from our solid state course, and they are written here. You have the change in the crystal momentum that connects both to the E field and the B field, and you have the velocity, which relates to the curvature of the band structure. And we took well, now you can say somehow it's maybe okay to look at the dipole acceleration. It's not entirely correct. You need to, if you want to do it better, you need to take into account some retardation effect also. But for this, it's maybe good enough to think about the dipole acceleration, which of course can be found very easily from these equations. Normally, people do not consider the B field. So the B field here is a new thing. And we then ask what happens. And that's shown in this view graph here. We took a dispersion similar to some zinc-based crystal, 30 cycle pulse and 2001 nanometer. The effect we look at here increases. If I crank up the wavelength, I will have more non-dipole signatures. Here in the top, it's a linearly polarized light field, and in the bottom, it's a circular polarized light field. And there are many curves here. Let's focus on some of the black ones here. That's the Fourier transform of the dipole acceleration in the polarization direction. And then we have the strong field approximation, which is on top, and we get odd harmonics because the crystal is symmetric. Then we have a non-dipole contribution here, which gives rise to even harmonics. So the signature here is that when you include non-dipole effects, it's very easy to understand. You break the symmetry because now there's suddenly a propagation direction also. It's no longer inversion symmetric. Therefore, of course, you get even harmonics. So, but we can also calculate the expected magnitude. In this particular example, I guess this is a challenge for the experimentalist to measure this type of stuff. It's 5 orders of magnitude, but maybe if we look at another material or crank up the wavelength, it could maybe be measured. So, okay, about the circular, it's also interesting. There are some particular selection rules, and you can derive this analytically using this non-dipole strong field approximation. And those selection rules mean that some of the even harmonics are not allowed. Now in the last part of the talk, more or less, I'll talk about correlation. And the idea is to take a linear chain of ions, like we heard this morning, and distribute electrons along that chain. And the most popular model from the condensed matter community to address this type of situation is the so-called Fermi-Hubbard model. So that's the one we take. So I come from AMO physics myself, so I didn't know about Fermi-Hubbard models. So in the case some of you don't know, I will tell you what it is. So it's this one. It's this with a hop on, and the hop has 2 terms. It has a hopping term and a correlation term, U. And the hopping term is basically just describing how you can go with the electrons from side to side. You see you kill an electron at side I plus 1 and create one at side I with a hopping term T naught in our notation. And this one here we come back to. So that's the hopping Hamiltonian. And if you transform into crystal momentum space, you can easily diagonalize this one. It will give the block band. And then you have the hopping term over here, which counts the number of electrons on a particular site. If you have 2 electrons on a site, you have to pay a price in energy, U, right? So if U is big, it's not good to be here, right? You want to distribute the electrons. So now we talk about harmonic generation. So it's the same again. If U here is small, it's like more or less what we have seen so far. Most of what we have discussed today in solids is with very low correlation. You use semiconductor block equations, use TD-DFT, you have very limited amount of correlation. And if you add U, you have to use a new picture, which is handy and very similar to what we normally use. But now instead of talking about electron and holes, you talk about duplons and holons. So duplons are quasi-particles where you have an electron pair, and a holon is one where you don't have anything, right? And then in this picture, you can describe the same steps that we like, namely creation and propagation of a duplon and recombination, right? Now, to see some data, we take some parameters here for frequencies and field strengths and number of cycles that are typical. And here that you have my some maybe experimental units over here and atomic units here. And we take the system parameters for the T0 and the A from a cuprate that has been studied previously. So these are not made up things. And then we treat U as a parameter. And if you look at these cuprate systems in the literature, you will have a range of U values from 0 up to 15. So you can have, in the extreme case, maybe 10 is more appropriate. So here's the first example. The first study we did was asking ourselves the question, what happens if I have a finite system compared to if I have a bulk system? And here you have, in the limit of no correlation, the finite system high order harmonic generation response, and you have the bulk high order harmonic generation response. Then we increase the correlation a little bit, and we see how the difference between the finite and the bulk spectra decreases. And the physical reason behind this is that if you have a finite system, you will have, and if you have low correlation, you have trajectories that go to the boundary, turn around, and keep being accelerated. And that's, of course, not present in the bulk system because you have periodic boundary conditions. So you can pick up more energy here in the finite system if you don't have a lot of penalty associated with the electron motion. But if we just add a little bit, and it's easier to see here, the U is so big that it's more difficult for the electrons to move. They're more like quivering a little bit. So you never have these long trajectories that create that big difference. So that was the first study. And now we have on the poster, this one with the doping. The standard setting for this Fermi-Hubbard model is that you have, say, L sites, and then you stuff L electrons into it. So this means you have, you can put one electron on each ion. That's the normal situation, but you could dope the system. In that case, you can have one more or one less, right? So that's what we wanted to do. I think I may come back to this later. And then we ask again, how can high order harmonic generation be used to tell us something about the level of doping? How is the dynamics in the system depending on how we dope the system, right? And to understand that, if you now take the half filling condition, you can put one electron on each side. And if U is very big, it's not easy to get motion going, right? Because it's very expensive to create a holon and a duplon. That's the so-called Mott insulating limit. So the Mott insulating limit is here, and if you have no doping, you see you get very little high order harmonics. But if you have other situations, you can get some, and there are some lines here, and these lines, for example, this one here, where you have very little correlation, is essentially just the bandwidth of the block band times 2.
The one that's the bandwidth is in my ordinate in the top figure. That is the bandwidth plus 2 times the bandwidth of the block band underlying it.
Thank you very much. So you can go and get all details from Thomas. In fact, these slides are also his, but anyways, that's so let me leave this slide now then. And as the final thing on the Hubbard model, I mean, we're exploring different mechanisms here and ask questions. What happens in the solid when you have a combination of correlation and other effects? And one of the other effects you have in a solid is that it's maybe not perfect lattice. You can have some imperfections. We try to show here, and how to model that. One way to model that is by adding a term here, which is in fact the same as people have used when they study Anderson localization. So it's a shift of the chemical potential at the sites. And what we were interested in here was to ask the question, how does this noise level and the amount of correlation play together? And that is what is shown here. And basically what you see, the take-home message from this one, I don't want to go into the detail now because I have to finish in 1 minute. The take-home message is that you can have cases where U is, say, rather big, kind of impedes dynamics, but then when you add the delta, the noise, you change the potential and you can certainly have a more favorable situation for dynamics. So they can somehow balance out each other, those two effects. Please see this one. And this is my last slide. And this is not, this is more like a teaser, and we already today heard a very interesting development. It's my understanding that this field where you can produce short electron pulses is really taking off now. You see very many interesting papers on arXiv these days. And this is a very nice situation for us as theoreticians, because it means, I mean, it's experimentally challenging, but it's also very interesting for theory. And the reason is maybe easy to see from a formula like this one, which is a formula saying what is the probability of measuring a scattered electron with a fine momentum. And here you have T-matrix elements, and those who have had scattering theory, you know what they are. But you normally never have it in this way of coherent contributions. So because you have a wave packet of an electron pulse that comes in, it's broad, you have many incoming momenta. This means that you can have many different KIs hitting the same KF. And that leads to quantum mechanical interference, and that's what is included. This is what somehow mathematically you see in this formula. This means that when you do the theory, it's very important to have the phases of these T-matrix elements correct, and you also have access to the phases. And that's something we never have in ordinary scattering. And then, of course, it's also interesting to use this in a pump probe setting. You can control the delay between an initiating laser pulse, initiating some photochemical reaction. You can come in with this type of probe afterwards. You don't have to rely on LID concepts and stuff like that. Thanks a lot for your attention.
Question, please.
In your about under some kind of model, did you look at the effect of spin? Because we used to look at this in arrays of quantum dots, and the big effect.
Yeah,
localization.
Yes, I mean, of course, spin is there, right? Yeah, but we did not. I mean, I mean, I don't know. Did you calculate some spin measures? Probably it's for the poster. I can't remember exactly what.
The only way to calculate spin measures is to ensure.
Yes, that's true.
So
yeah.
No. Not really. The main issue is there's asymmetry on the spin inversion within the system. So you take all spins, flip them, and you see no difference whatsoever.
Yeah.
So it's mainly in.
I mean, doctors.
Yeah.
And you used most everything you did was first order in 1/c.
Yes.
But I mean, we have the fully relativistic Bojer solution,
Yes.
which is exact and simple.
Yes.
That's the way it was written down by Bojer.
Yes.
So why not use that?
No, that can also be done, and of course, if you go back in the literature, there you find the old paper by Ries where you can find the shifts hidden. So that's one approach. I like to take this. It seems to be good enough, and it's, in my opinion, simpler, and it's also probably simpler to implement also in TDSE type solvers.
Okay.
Yeah. So, but otherwise, I mean, certainly, yes.
More questions or comments?
So in the experiment, they found shifts not in propagation direction, but against. So do you see this in your theory?
Yes, I mean, that's a good point, and I think those of us who have done this type of stuff know that you get shifts with this type of SFA that can be in the wrong direction sometimes, and the origin of this is the lack of the Coulomb attraction. So if you have if now I have very low in the electron coming out here, it can feel the Coulomb and go to the other side. And I think you did some semi-classical modulations yourself about this effect some years ago. Yeah. Yeah.
Any more questions or comments? Well, if not, let's thank Lars again.
What should I do?
Yes.
No.
So the second speaker in this session is
And
Francoise Remacle. Sorry, my eyes are
how does it?
tired. And the title of the talk will be visible in the second.
Yes.
So it will be about electronic coherence build up and attopulse shape, the entanglement between electronic and nucleus degrees of freedom.
Okay.
Please.
So, good afternoon, and thanks to Carla and her team for organizing this meeting. So I will talk about the role of electronic coherence and how they can be used when they are produced with an attopulse to shape the entanglement between electron and nuclei in molecules, and what is the influence of this entanglement on the force on the nuclei. I had prepared all kind of advertisement for the posters, but since it will be tomorrow, I think for the sake of time, I can move on. So as we already heard several times, attochemistry is different from femtochemistry and what you can get with exciting molecule with longer pulse. And the major difference is the fact that we have a broad energy bandwidth because the pulse is short, and it's typically then we are going to excite simultaneously several electronic states which fall in the bandwidth of the laser in diatomic molecule. It's a cut here in the potential energy surface of norbornadiene. And the point then is that we are going to entangle the motion of electron and nuclei already at the excitation step when we use such broad laser pulses. And then it means that then we are going to, when the dynamics unfold, the entanglement can be modified by the non-adiabatic coupling, but it will still be a major cause and a major screw to control the dynamics, to control how we entangle at the initial state. And so this is what we set up to do, right? We would like for many years to be able to control chemical reactivity by controlling electrons. And so we mean that we want to exploit a non-equilibrium electronic density that was created by building this superposition of electronic state at the initial excitation. And we now want to show that this allows us to shape entanglement and also to shape the force. So we could show some control in diatomic system, in LIH. More recently, we showed also in N2. And as I like to show also, we can have control on larger polyatomic system, like in 4-carbon ring closure from norbornadiene to quadricyclane. And there we could show on the computer that by controlling the linear polarization of a short 2 femtosecond UV pulse, so these are the UV pulse in the deep UV that became recently available, we can really control the dynamics of bond making. And for me, it's more interesting to make a bond than to break a bond. And so what we showed is that if we we use a linear polarization that is perpendicular to the 4-carbon ring that we want to form, we will get a higher yield of quadricyclane at short time. I say short time because it's quantum dynamics that we need to use to show this control. And so we are limited in the number of degrees of freedom, but also in the amount of time during which we can integrate and conserve norm and have something reliable. So it's a computation for 3 nuclear degrees of freedom that essentially are the closing of the bending angle, the elongation of the double bond here, and a kind of a distortion to capture non-adiabatic interactions on 8 electronic state. And what we could show is that when we polarize the pulse perpendicular to the 4-carbon ring, we create a coherence between 2 excited states, S3 and S2. This coherence evolved in the configuration space, and the point is that it is beating with a period of 20 femtosecond and correspond to a motion of the electron in and out the old and the new bond. And so this period is commensurate actually with CC period, vibrational period, and this seems to control the fact that we get a higher yield in quadricyclane compared to another pulse where we polarize parallel to the new bonds and where we just excite S1 and get the typical non-adiabatic single electronic state dynamics. I also wanted to come back to this recent work we did on the ultra-fast Jahn-Teller rearrangement in the methane cation. Here it's another effect of coherence. So as you probably all know, when you suddenly photoionize the neutral, you get to a point TD here that is unstable. And so you have a very fast structural rearrangement that is driven by non-adiabatic interaction between the 3 lowest electronic state of the cation, and that involve going to all kind of distortion of the TD form to D2D to C2V. And the point is that when you look now at the quantum dynamics, and here we have a 2D model for 3 electronic state, but we did include the random orientation of the molecule with respect to the field. And we see that depending on which kind of energy we use to photoionize, here it's photoionization, the neutral, either the 11th harmonic of the 800 infrared pulse or the 9. The difference between the two is that HN11 will excite D2 significantly. So we built electronic coherence between D2, D1, and D0, and we get a very rich dynamics of population as a function of time, not only a very rich dynamics, but also a very large isotope effect. You have here in dashed line CD4 and in full line CH4, while if you just essentially photoionize to D0, to D1 and to the ground state of the cation, you have very boring dynamics of the population and essentially no isotope effect. And then we wanted, doing this, we were motivated by the very early results of Jon Marangos on the isotope effect on the harmonic yield in methane. And so we computed the autocorrelation function of the initial state. We follow the paper of Manfred Lane, and we look at the ratio of the autocorrelation function for the 2 isotopes. This is what I show here on a rather long time scale. And you see that when we populate D2 with the orange line here, we have oscillations of the ratio, and we have a very different behavior from using a lower energy to photoionize. And if we look now at the time spent by the experiment of Jon Marangos, we get here a ratio that is 2.6, while what was reported at the time was 3. But what is interesting for me is that we can really trace this to the fact that the autocorrelation function, and here we average over 8,000 orientation of the molecule, is sensitive to the electronic coherence. This is the term that I show here in red. And so if we do not include on the computer this term in the computation of the ratio of the autocorrelation function, we get here the dashed line, and you see our isotope effect is gone, essentially. And so it means that we have a very large effect of this D2 to D0, D2 to D1 electronic coherence in controlling the early time dynamics of the structural rearrangement in CH4+. This is just to show the wave packet, how the electronic coherence localizes, and there are also lots of differences here. And we also looked at strong field ionization, and we get essentially the same picture. So this brought us to the first point, that we need, of course, a full quantum methodology to see these effects. And so we integrate the time-dependent Schrödinger equation on a grid for several electronic states. And we have two terms that will entangle the electronic and nuclear motion. As I said before, the interaction in the dipole interaction with the pulse, and the NAC terms that are driven by the nuclear motion. And then if you want to rationalize the control that you can get, or understand how you could control knowing that you have entangled motion, you need a measure of entanglement. So what we did is to use a measure that is called the Schmidt rank. So at the end of the pulse, we have a Born-Yuan expansion of the wave function. So we have a superposition of a very large number of separable components to describe the wave function. If we would have only one term here, we would have a non-entangled wave function, and it would mean that the Schmidt rank is equal to 1, meaning that we can factorize these amplitudes into a product. One amplitude depends on the grid, and one amplitude depends on the electron. As soon as we have more than one term here to fully describe the wave function is entangled. And so what we did to compute the Schmidt rank as a function of time is to matricize the column vector of the Born-Yuan amplitude into a rectangular matrix that is has Ng rows, which is the nuclear grid, and N-E columns, which is the number of electronic states in our problem. And you do SVD on this, and then you know that the rank is maximum equal to the number of electronic states, the smaller dimension of your matrices. And so we get an expansion in maximum N, the number of electronic states for the number of terms. And we have separated here each term into a nuclear singular vector, an electronic singular vector, and here you have the weight of this separable product. Then you see that we got a massive compaction of the wave function. We start with hundreds of thousands, or at least tens of thousands term, and we get now the number of electronic state terms, or a dozen, essentially. And you see also that we can even compact further, because if we decide that we want to describe the wave function up to a certain accuracy, so we don't want an exact expansion, we just need to define the threshold, and we will have a smaller number of terms. We have implemented this on two molecules that are our preferred toy models, N2 and LIH, and they are very different in terms of the features of the electronic state, in terms of the strength of the non-adiabatic coupling. Also, we excite with a UV pulse here in N2 to a superposition of essentially two states, the valence and the Rydberg, and so we have bound dynamics. So this is the dynamics of the population. And in LIH, we go to dissociative states. And so we have first, at the exit of the Frank-Condon region, very rich transient dynamics. And then we just move, each wave packet move on its own to the dissociation limit. So what I show here is the principal values. So the square of the weight of each of the components after we have matricized the wave functions. And you see that we get essentially a component that will describe the ground state, and then two oscillating components here that essentially will describe what happens to the valence and the Rydberg states. While here we get a very monotonic, much more monotonic time evolution of this principal component. And you see that they appear here in a sequential way, right? As my wave packet is moving, I need more and more terms to describe the dynamics correctly. So here I even see timescales that are reproduced by these coefficients. So we can define a threshold for the accuracy of the different observable that we want to reproduce. And essentially with 3 terms, we reproduce even observable like the full polarization that really depend on the electronic coherence, right? And very sensitive to those. We have also an interpretation on the meaning of the singular vectors. For sake of time, maybe I will not be too detailed. I am happy to answer questions, but essentially, this is the electronic singular vectors, and they will describe how many electronic states you need to describe the wave packet in a given region, actually, of the R coordinate in our case. So you see that because here my nuclear singular vector is localized in the Frank-Condon region, during the excitation, I will have one component that describes all the electronic states that fall in the Frank-Condon region. But as time moves on, as I already say, you have a more complex meaning of this singular vector. Let's put it this way. And we can describe isotope effect, but I will not talk about it now. Now, this method is not limited to 2D. You can have many a multi-parted system in the language of quantum information, right? Not only a bipartite system. In that case, we will need to use high order SVD. So we did it for the CH2 problem, and we need to get a core tensor, and this is the separable terms, separable singular vector in the 2 nuclear coordinate and in the electronic state. And you see that with 2,000 terms, we can describe 99% of the trace of the density matrix of the system up to 50 femtoseconds. So we again get a major compaction. And not only that, we can also recover not too badly the wave function. So here I am showing at 1 femtosecond how we recover the wave function with only 190 terms in the expansion. Then it brings me to the last part of my talk, which is very recent result. We wanted to understand how entanglement can be used to shape the force of the nuclei. So I am talking about a semi-classical force, right? We don't have an operator for the force, but we can still compute the mean value of the force, the mean being on the vibronic wave packet, and using the Ehrenfest theorem, it is the mean value of the commutator between the gradient and the full Hamiltonian. And when you do all the math for the commutators and you use a adiabatic electronic state, you end up with 2 kinds of terms. A terms that depends on the potentials. This term is rather well known, right? It's the mean value of the gradient of the potential. And you have also the mean value of the commutator of the NAC with the potential. It is also a known term. It appears in the semi-classical dynamics description when you want Ehrenfest dynamics, for example, when you want to include the effect of non-adiabatic coupling. And then we have 2 terms that depends on the dipole. So this is where you shape the force with the initial state. And again, they are similar to those, right? Mean value of the gradient of the full dipole and mean value of the commutator between the dipole and the NAC multiplied by the electric field. And so this is where you see that you can have a force. If you have NAC in the Frank-Condon region, you will have a rather large force that will come from this term. Okay, and this will shape your initial kick on the nuclei. So we computed all this term in LIH again. And so we have essentially 4 terms. So we see here is the vector on the grid point and on the electronic state. And you see that all the terms except actually the gradient term, they will depend on electronic coherence. They will be off diagonal in the electronic index. And so here we show how we can shed the force by controlling the CP of one cycle IR pulse. So we have multiphoton ionization to the same set of states that I showed before, but here it's not the same kind of excitation. It was a UV 1 photon. Here it's a 3 photon IR. And if the CP is equal to 0, you have the maximum of the electric field that points to the lithium. If the CP is equal to pi, you have the maximum of the electric field that points to the hydrogen. You have a control on the population. We have shown this already in several papers. If CP is equal to 0, you essentially access S4 for this kind of pulse with S1 here and a little of S2. Well, S3, sorry, that is rising due to non-adiabatic coupling. While if you use CP equal pi, you have a lot of S1 with much less of the others. Let's put it this way, and this we understand from the transition dipole values. This is because of the alternance of the polarity of the excited state in LIH. Now, this is the total force here, and you see that it is radically different, right? I get something that is not very large for CP equals 0. I get a very large force that is pointing to the hydrogen in the case of CP equal pi. This is what we were suggesting should happen from purely electronic dynamics. It's almost 15 years ago in one of our earlier papers. And we can understand why it is close to 0. Here it's because the force that comes from the gradient, which is this blue line, is opposite sign of the force that is coming from this term that is really not classical, that is the mean value of the commutator between tau and mu. And so you see they neutralize essentially. So this is why we get this. While here they go, we have in the same direction this blue line and this one. And so, and this one, sorry, this term, tau with V, and this is what gives you a very large value here. So you see that these terms, even during the very short pulse, can really act in different directions, and that you can essentially control this here by the CP or by the polarization, or even probably with the duration of the pulse, which is something we didn't try. And then we can also look at the force after the pulse, okay? And this is a complicated slide, but I have still a few minutes. So I show here the value, the dynamics of the population for LIH, for the two value of the CP. And we saw that we are going to use isotope substitution. So look at LIT so that we see the effect of the mass, right? And how it can probe the force on the nuclei. So here I report the dynamics of the population for LIT for CP equals 0 and CP equal pi. And you first see that we have very different dynamics right after the pulse for the two CP, but also very different when you have an isotopic substitution. And then here I am showing the force, the total force. This is the black line that oscillates very fast because I have this mean value of the commutator between tau and the potential. This is the two terms that are acting after the pulse are the mean value of the gradient and the mean value of the commutator between tau and mu. And this one oscillates very fast because of the electronic coherence between excited state, while the mean value of the gradient is very slowly oscillating because essentially it varies with the vibrational motion of each wave packet that is bound, and it's the ground state and the first excited state. And so you would say, okay, your force oscillates so fast that you will not have any effect on the nuclei, right? But then if you smooth this, you start to see what appears is the electronic coherence between excited states. And then they beat on a much longer period, right? Because the spacing are smaller. And this is really when you can control the force and the NAC and the population transfer, because you need that you get electronic spacing that become commensurate with the motion of the nuclei around the NAC, right? You want that you cannot decouple electron from nuclei to have population transfer. And so we see this very clearly, and you see even that this period, because it is electronic, will not vary with the mass. Okay, so if I have fast electronic coherence, the mass doesn't change then because it's an electronic property. And so we decided to Fourier transform the force. And then by Fourier transforming LIT and LIH, we can see which period are moving. This is vibrational period, and which period do not move, and this will be electronic period, the periods of the electronic coherence. And this is the result I showed here. This is LIH, yeah, this should be 0, sorry. So it is LIH 0, LIT 0, and you see that we are moving with the right shift, which is 2.5, should be a square root of 2.4 here for the vibrational period, while the NAC here are not moving and correspond to the energy difference between the electronic state. And if you look now at the high frequency part, you get in the force the fast beating electronic coherence between the ground state and the electronic state. I am essentially done. So I showed that we can get controls through building electronic coherence in diatomic system, in polyatomic system. And essentially it's because we untangle electron and nuclei. And we now want to have tools to have a rational design of this control. And it means to analyze entanglement and understand how it develops, but also to understand how we control the force and how entanglement will affect the force on the nuclei. Thank you very much. Thank you very much.
We have 4 minutes for some questions and comments.
Yeah, very interesting, Francoise. So I would like to clarify one thing to make sure that I properly understand. So you say on the one hand that it is the entanglement that shapes the force on the nuclei. Mm-hmm. And then when you analyze the forces on the nuclei, you find evidence for electronic coherences. But I am correct, right, that these electronic coherences are basically within single terms within your Schmidt decomposition, right?
Electronic coherence is kind of ill-defined in a way, right? Because it depends on my representation, right? My electronic coherence are between adiabatic states, right? And now I don't have time to show that, but if you look in the singular component, they are also not eigenstates. So there are some kind of eigenstate of this matrix, how I choose to decompose to build my rectangular matrix. And there too, we have electronic coherence, but between the singular component, right? I can change representation. And even if I have true coherence, if I have the eigenstate of my full potential of electron and nuclei, I will have coherence in my density matrix, right? And this will be more or less the one I care about. Okay, so I don't know if I have answered your question, but depending in which basis I will look, I will see a different manifestation of my electronic coherence. And so it's easy for us to think of electronic coherence between adiabatic electronic state and between vibrational state in a potential. And they are a manifestation of electronic coherence between true eigenstate of my system. And I will have all kind of distribution of spacings, and I will have coherence there too. Do I answer? Okay.
Nice talk. In your singular value decomposition of LIH, I think you said that there are 3 states basically.
Yes.
Values. But one of them is close to 1, which is the one associated to the ground state, because
yes.
it has a population close
Yeah.
to 1.
Yeah.
So all the others are very small. Yeah.
I mean, the values of the weights are here. So it is like 0.7.
Yeah.
Yeah.
Okay. So in fact, I mean, when you make the comparison of the wave functions, the full wave function with the one you would get only by including these 3, it includes the ground state. So,
yeah.
So my question is, if you remove the ground state, which is, how this comparison would look like?
It still look quite good, because I mean, okay, here you have, for example, I look at the polarization. Let's look at the coherence between state 4 and state 2. So it is not influenced by ground state, right? And I am getting essentially exact with the blue. And blue means 3 terms. 1 + 2 + 3. If I only take 2, you see that I am off. Okay, but you see, so, okay, and I didn't try, what you are trying to tell me, try 2 and 3 and remove 1. I'm not sure, but okay, yeah, I get your point, yeah.
I have a related question, maybe I didn't understand something. But you said at some moment that you can do your singular value decomposition for 3-partite systems?
Yeah.
I don't think that the Schmidt decomposition...
No, it's not Schmidt. I don't mean it's Schmidt.
What do you mean by that?
I mean that I built a tensor.
So it's like in matrix products. Like
Yeah,
tensor,
and I want to use this for matrix product. Yeah. But it's a pain to do. Yeah, and it doesn't scale.
Because for the true, so to say, Schmidt decomposition...
It's true. You are right. Yeah.
Any more questions? Or comments? Well, if not, let's go on. The next speaker is thank you very much. And the next speaker will be Andrew Maxwell, who will be talking probably about vortices, I guess.
Not this time.
Oh.
No, about spin-over coupling and other non-relativistic effects.
All right.
Where's the pointer? Is this one? Okay.
Yes, relativistic and spin orbit dynamics at non-relativistic intensities in strong field ionization.
And Maciek very nicely read the title for me. Because I'm the last talk before you in the boat, I'll try and be as brief as I can be. So this is about spin orbit dynamics and other relativistic dynamics at non-relativistic intensities in strong field ionization. And the main motivation for looking at this was initially looking at spin in strong field ionization. Of course, at relativistic intensities, there's many nice treatments of spin, such as the relativistic strong field approximation or treatments of the Dirac equation. But in our typical tunneling picture for non-relativistic intensities, we of course have spinless electrons, and we don't tend to consider spin. So in this talk, I just want to kind of add a little bit to the conversation of how spin will enter and how reasonable is it to ignore it. So first of all, I want to kind of split the possible effects that you can get. So there are static spin effects, which have had a fair amount of work looking at them. And this is when you have, of course, have a larger atom with appreciable spin orbit coupling, and then a strong field laser can essentially cause spin polarization. So you can have more spin up in one energy than spin down, for example. But what I want to look at in this talk is dynamical spin effects. So as we look at longer wavelengths, then the returning electron wave packet can gain a lot of speed and can gain high angular momentum and get very close to the target. And so maybe we can see some appreciable spin orbit coupling effects here. So the motivation behind this is imaging processes such as laser-induced electron diffraction, and also to a less extent photoelectron holography, where you strong field ionize a molecule and then you have a recolliding wave packet due to the oscillating laser field, which can be used to diffract off a molecule and work out the positions. And so, of course, getting spin orbit coupling right here would have a lot of relevance. And in lead, we look at long wavelengths, like 1 to 3 microns, high electron, and you get high electron recollisions with high electron photoelectron currents. Okay, so, but I kind of want to talk a little bit about the background works that motivated us to study on this, and these are kind of in the direction of these static spin effects. So people have shown this work before, but I'll go over it again quickly. Essentially, Ingo Barth and Olga Smirnova had this 2013 theory paper, which through circular strong field ionization, they could show spin polarization effects due to this fine structure splitting and spin orbit effects. And then this was later measured using a Mott detector where you could measure this spin polarization. And so, as I said, though, we want to look at these dynamical spin effects. And to do this, we're going to use a semi-classical model. So we're going to use the CQSFA. And so first of all, I'm going to kind of briefly go over the construction of this without spin and in the non-relativistic regime. So this is the S-matrix approach, which starts from the same point as the S-matrix SFA, and we have this well-known S-matrix transition amplitude where you have an initial ground state and a final continuum state with a momentum PF. And then the difficult object to unpack here is the time evolution operator. And there are various approaches to looking at this, but here we use a path integral approach. So that is, if you have a propagator for going from state QA to QB, you can do a sum over all possible paths and do a functional integral over the semi-classical action. So if we do this for this transition amplitude, we get these two functional path integrals summing over all possible paths, and we get the semi-classical action here along with the dipole matrix element. So the semi-classical action has a potential term, a kinetic energy term, and because we're looking at momentum propagators, we get this P dot R term, which is essential for getting the phase right and the dynamics. Now, we can't solve these functional integrals directly, so we have to use some method to do that. And one approach is to use the saddle point approximation. And the nice feature of the saddle point approximation is you get semi-classical equations of motion out, of course, and then we can simply sum over these solutions instead of computing the functional integral. So the semi-classical equations of motion we get in this setting are the well-known ionization equation, which is very similar to the SFA ionization equation. And we get, of course, complex solutions in time, where the imaginary part, of course, is related to the tunneling. But we also get, coming out of the semi-classical approximation, Newton's equations of motion, which govern the trajectories in the continuum. And then if we put this all together, we get the final transition amplitude, which sums over these solutions, and we have the semi-classical action, which is evaluated at these equations of motion, the solutions of these equations of motion, the dipole matrix element, and then we also get this prefactor, which comes from doing the saddle point approximation to the functional path integral. And it has a stability matrix, which essentially penalizes trajectories which are chaotic or unstable, so are sensitive to their initial conditions, and also a Maxwell index, which is very important for getting the phases right. And then from doing the semi-classical approximation on the time integral, we get this prefactor, which you also have in the SFA. And I don't know if the poster session is still after this briefly, but I just want to do a brief shameless poster box. So master students, Madsen and Mill, have been working tirelessly on different things related to CQSFA. So I do encourage that you go and check out their posters. So one of them is looking at the development of the CQSFA, inclusion of Maxwell phases, and the other one is looking at chiral imaging and looking at chiral molecules of the CQSFA and using electron vortices for chiral imaging. So do check that out. Okay, so if you solve these equations of motion, we kind of vaguely categorize them into 4 categories that aren't exhaustive, but they kind of give us an idea of what's going on. And I'll just briefly go over them here. So we have in blue, what we call imaginatively orbit 1, which tunnels out on this side and then goes directly to the detector. It's kind of analogous to the direct SFA orbits. And then we have these 2 and 3, which tunnel out on the opposite side to which they end up and are essentially forward deflected past the target ion. And then we have the rescattered trajectories that we're interested in this work, because these are the ones that might pick up some spin orbit coupling. And so this one is a laser-driven rescattered trajectory that tunnels out here, and then the laser drives it into the residual ion. And it's essentially the same as the long and short trajectories that you get in the high-order ATI or HHG, but it essentially accounts for the Coulomb potential along its whole length. But it takes a similar form. And then we have trajectories such as this, which is a directly recolliding orbit. And essentially, its initial conditions are such that it just immediately recollides with the residual ion and scatters very hard off it. Okay, so now putting this all together, we can compare with numerical methods such as the single active electron TDSC method, QProp. And so on the left here, we have a 4-cycle sine squared pulse, and on the right here, we have a 6-cycle sine squared pulse. And at the top, we have these TDSC QProp calculations, and in the bottom half, we have the CQSFA calculations. So you can see we do get pretty good agreement. And this good agreement comes from including now short pulses, the Maxwell phases, and also including solutions that we didn't include before. Really, you can see the main disagreement comes along classical boundaries where the approximation essentially breaks down. But we get very good agreement of these high energy rings, which is what we're interested in today, because we're looking at these rescattered trajectories. So I want to kind of zoom in on this point here, where we kind of are sampling a single momentum point and look at the trajectories that we get there. So here I'm plotting the velocity of the different trajectories, the distance, and the phase. And on this plot, I've also put the 6 cycles E field, plotted the ionization times on it, and then you can see the velocity here evolving with time. And you see very large spikes in velocity as you get incredibly intense recollisions. And actually, the units here are in terms of the speed of light. So we're getting superluminal velocities, and this is simply a result of the fact it's the non-relativistic Schrödinger equation. And these aren't like rare, weird occurrences for the semi-classical model. We get them occurring in quite a big region in the rescattered area. And so it means, you know, a substantial amount of the wave packet has a group velocity going above the speed of light. And this is due to the fact that they probe the target so close. So they go to 10 to the -5 atomic units. And then this, of course, results in a very high spin orbit phase, so essentially we've got the phases here. In solid, we have the kinetic energy. In dashed, we have the potential energy. And then we have dot dashed the spin orbit phase. And this, in this case, is exceeding the phase due to the potential. And this doesn't really seem right. Now, all of these dynamics within a Bohr radius of the atom are taking place within a single attosecond. So that it's very intense and very fast. So really, we need to do better, and we need to include relativistic corrections to our theory. So that's what I'm going to take you through now. So of course, if we expand the Dirac equation to orders of 1/c², we get this Brett-Pauli Hamiltonian. But because we're only looking at 1,600 nanometer wavelength, we can still apply the dipole approximation here. And so this allows a length gauge formulation of the Hamiltonian. And then this can be written in the following way. And the important terms here are a quartic correction to the kinetic energy term, sometimes called a mass correction term, and also the spin orbit coupling term. And that's what we're going to focus on. Now, in order to look at this from a path integral point of view, for quite some time, it was difficult to include spin in path integrals. But then with the tools afforded by coherent states, we could use coherent states path integrals. And so you can essentially use these things called coherent spin states, which map the complex parameter Z to superpositions of spins. And it has the following resolution of the identity, which we can use to construct a path integral. And then this allows us to take propagators that start with an initial Z and an initial P to a final Z and a final P. So now we have a well-defined route in terms of how to describe our transition amplitude with path integrals. And so we start with an initial state with quantum numbers J, M, J, and we end in a final state described by ZF giving us a final spin and PF giving us a final momentum. And then as before, we iterate the Dyson series and then insert a resolution of the identity operator in momentum. But then what we want to do is essentially get a propagator with an initial Z here. And to do that, we need to commute the spin components from this JMJ initial state into here. And we can do that by expanding it with a sum of the quantum magnetic number. And then we can get this Z here. And so now we're in a position to insert essentially a path integral formulation, which we can do here. So now you see we have a path integral over position, momentum, and the spin, which is given by the Z integral. So putting this all together, we now have a transition amplitude that describes the spin orbit coupling and non-relativistic effects as well, relativistic effects as well. And the action now has some additional terms. So of course we have the spin orbit coupling term, we have corrections to our kinetic energy, and then we also have this term which is important for essentially getting the phase of the spin correct and the semi-classical motion, equations of motion for the spin correct. Okay, and so as before, we need to solve the functional integrals, but instead of just directly applying the saddle point approximation, because we're looking at a very simple target, hydrogen, we can apply the weak coupling approximation. And so essentially we can pull out the spin orbit components into a single transition amplitude where we integrate the spin orbit action over Z, and we can compute this analytically. And this gives us the following equation. And then in the transition amplitude, we can apply the saddle point approximation that we applied before and insert those solutions into this transition amplitude. And this is a weak approximation because what it means is that the spin orbit coupling depends on these trajectories, but the trajectories do not depend on the spin orbit coupling. And it's valid as long as we have that the spin orbit phase is much less than the rest of the action. So this equation looks kind of complicated for the spin orbit dynamics, but it's not really, it's just dependent on these two parameters, A and B. And A essentially is giving us spin preserving transitions, and B is giving us spin flip transitions. So now we can define some measurements that would be interesting to look at. And so far we've only considered well-defined initial and final spin states, but we can average over the initial spin or average over the final spin or both. And so obviously we can do basically incoherent sums of these. So here we're averaging over the initial spin, averaging over just the final spin with the initially aligned spins, and then here averaging over both. And then from this, we can kind of think of an interesting measurement, and that would be, we define this quantity, which is essentially the spins aligned in the x direction minus unaligned spins. And this is interesting because we are looking at trajectories that are fixed in the ZY plane. And so that means the angular momentum is only in the x direction. And so this is why we would, in this situation, want to consider aligning the spins in the x direction. And then our spin orbit dynamical equations can actually be heavily simplified and in fact solved exactly where they're given as cos and sine of this semi-classical action for the spin orbit coupling. And then because we're in a weak coupling approximation, we can expand this in a Taylor expansion and get that essentially that spin flips will be of order S0 squared, S spin orbit squared, and that means that there will be 0. And this is of course in line with what we would expect because we won't get any spin flips for the hydrogenic system. However, this quantity that we defined here, which is the difference between aligned and unaligned spins, sorry, aligned in the x direction and completely unaligned spins, will be linear in this spin orbit phase. And so we expect a small effect there. Just one final thing is we can use relativistically corrected Kepler hyperbola to actually analytically compute the spins, especially because it goes in a very Coulomb dominated region. So just to show you quickly, we essentially get this, and this agrees very well with our numerical results. And now finally, I just want to show you 3 key results that we get from computing this theory. So I just want to add an additional row to the figure I showed you before, where now we include the kinetic energy corrections. And of course, we now get that the trajectories are under the speed of light, so follow the laws of physics, which is thankfully very nice. And they actually probe the core much less strongly, so a factor of 100 less strongly. And then the spin orbit coupling phase is reduced by a factor of 10. So that is maybe giving us a lesson about including these kinetic energy corrections when computing the spin orbit phase. Yeah. And now I want to isolate the effect of these kinetic energy corrections, or the mass correction term. So on the left, we here have included them, and on the right is the difference between including them and not including them. And then we have 2 lineouts, one very close to the axis, one a bit further away from the axis. And you can see when you include them, you kind of boost the probability on the axis. And it actually, the difference goes up to about 50%. So it is an appreciable difference and something that should be taken into account. And we can just explain this by actually a reduction in the sensitivity of the trajectories to the initial conditions. Whereas when you go slightly further away from the axis, the situation actually reverses, so that you get kind of slightly diminished probability. And this is actually when you don't have backscattering, you actually get an increase in the sensitivity of initial conditions. And finally, I just want to isolate the effect of the spin orbit phase. So on this left column, we have not included the kinetic energy corrections. On the right column, we have included the kinetic energy corrections. And if we don't, and then we're plotting this parameter where we align spins in the x direction minus the unaligned spins. And you can see in this left column, on this line out, we get differences up to 40%, which in theory would be measurable. But on the right, as soon as we include those kinetic energy corrections, it goes down by over a factor of 10, and we essentially get no effect from the spin-orbit coupling there. So now I will sum up. We introduced an updated version of the CQSFA, which can now give very good agreement with the TDSE, and then showed how we can incorporate spin-orbit coupling and other non-relativistic effects. What we found is there are big differences for the kinetic energy corrections for the rescattered electrons, and that the spin-orbit phase is massively overestimated if the corrections to kinetic energy are not accounted for. So in terms of an outlook, for accurate treatment of these rescattered wave packets, relativistic corrections should be considered. And this can help with the production of laser-induced electron diffraction or photoelectron holography. In future work, we would want to look at bigger targets where spin-orbit coupling definitely will play a role. And so we'll add a coupled channel model, and we can get spin flips and things like that. We wanted to keep it simple at first, but it would be nice to go to something more complicated. And of course, to do that, we'll probably need to go beyond this weak approximation and instead do a full saddle point approximation to the spin. And then we also want to look at longer wavelengths, and so we'll also include the non-dipole terms in order to do that. I just want to thank the organizers for giving me this opportunity to speak, and also thank those involved in this work and similar projects.
Thank you very much, Andy. We have now 5:25, so we can have maybe some questions there. Okay, please. Any question or comment?
People want to go to the boat.
So the posters, there is nothing today, or I mean, we'll have.
Just called the boat. I'm sorry that I was going up out after talk, but just
No, it's all right.
see if we can be a little bit late. There is pizza in their posters, but I don't think this is something we can win.
Okay.
If I want to tell you how, but I have requested poster boards for tomorrow so that we continue the discussions, because I don't think it's fair on the people who have prepared the posters. And one issue is easy to get to the boat. It's 20 minutes. What you have to do is Houston Square, and then you just take and directly, you don't have to change or anything, and you end up in Westminster Millennium place.
Okay.
And I've called people to see if it's okay that we are late. I'll catch up with your talk, I promise. Because it was very social, but and I have a few questions as well.
Sure, yeah.
You want a question now?
Now, I don't know, because I wanted to know about the supraluminal spikes.
Oh, yeah, sure.
To caustics, but you want to outside and discuss. Because I mean, one difficulty that we had without including any kind of correction in the CQSFA, because we have also done a forward version of that in hybrid, as you know, is that we get a lot of caustics, which are to a certain extent exaggerated, and we get also those spikes.
No, I mean, it's not an effect of caustics. I mean, you can be far away from the classical boundary and you get superluminal trajectories. You can in fact I did do some kind of histogram of the maximum velocities, and there is a substantial proportion when you solve the non-relativistic problem that are above the speed of light.
Okay.
It's just because we need to solve the relativistic corrected equation.
Okay, but this is not related because I mean.
Well, I mean, at the caustics, they're very, very strong as well, but they definitely were not only at the caustic, and they're actually along the axis near the polarization axis rather than going along the side of a caustic. So if you kept going along the caustic, they actually at a big enough angle away reduce to below the speed of light.
Okay, I'll talk to you later. But anyway, thank you.
Any more question or comment? It doesn't seem to be the case, so let's thank Andy and Lars.